Welcome to the deep dive. So today, we're looking at a scenario that I think every developer out there dreads.
Oh, absolutely.
You know the one. You've written this beautifully clean asynchronous code. You've optimized your algorithms, but your application is just
Completely frozen.
completely frozen. Yeah. So whether you are an experienced engineer prepping for a big performance audit, or just someone curious about why your favorite website's loading spinner sometimes just locks up entirely, we've got a custom-tailored deep dive just for you today.
Yeah, we are diving into a really fantastic article by software engineer Aaron Rose. It's titled The Secret Life of JavaScript, the Microtask.
Such a good title.
It really is. And the mission here is to decode the hidden rules of JavaScript's event loop. We really want to uncover that aha moment of why asynchronous code isn't always the silver bullet that developers think it is.
Right, because we rely on async code constantly to keep things moving.
Exactly.
Ah.
But it turns out it can actually be the exact thing that freezes your user interface.
Which is wild to think about.
Yeah.
We're going to demystify the magic behind the screen today, and we'll do it without getting bogged down in super dense jargon.
Please.
So Rose sets up this incredibly relatable scenario. He frames it around a developer named Timothy. And Timothy is just staring at his dark mode IDE, totally frustrated.
We've all been Timothy.
Oh, 100%. So Timothy is dealing with this massive, heavy data set on the front end. And he does what, conventional wisdom tells us to do.
Right, he pushes all that heavy math into asynchronous promises.
Exactly. He assumes that this is going to free up the main thread to render the UI. He even wants to show this CSS loading spinner while the data processes. So he throws in a set timeout with a 0-millisecond delay.
A classic move.
Right. He fully expects it to force the spinner to show up first, execute immediately, and then the heavy processing can begin. But the spinner just sits there. It's a static gray circle. It refuses to spin.
And it's such a classic trap because Timothy fell for this really common flawed assumption. He assumed all asynchronous code gets treated equally by the browser.
He thought it would just politely alternate. Like, oh, I'll do the set timeout, then I'll do a promise, then I'll spin the wheel.
Yes. But developers frequently conflate the concept of asynchronous with non-blocking, and they don't realize there is a strict, completely invisible hierarchy at play under the hood.
Let's break that down a bit, because to understand why Timothy's screen froze, you kind of have to look at the environment JavaScript operates in, right?
Yeah. So unlike languages like Java or C++ that can just spin up multiple threads to handle background tasks simultaneously, JavaScript is strictly single-threaded.
One single lane of traffic.
Exactly. There is only one main thread handling both the execution of your logic and the rendering of your user interface.
So the call stack is essentially the browser's immediate to-do list. It just executes whatever function is currently sitting on top.
Right. And when Timothy's code runs, he assumed that by wrapping his heavy data processing in promises, he was taking that work off the immediate to-do list.
Giving the browser some breathing room.
Yeah, allowing the browser to squeeze in UI updates like his spinner right in between the mathematical calculations. But like we said, there's a strict priority system determining what gets pulled onto that call stack next.
And understanding that system is literally the key to preventing locked UIs. Which brings us to my favorite part of the article.
The coworker.
Yes. Margaret. Rose introduces this coworker character, Margaret. She rolls up with a dark roast coffee, a whiteboard, and just drops this perfect real-world analogy.
I love Margaret. Her analogy is brilliant. She essentially compares the event loop to a nightclub bouncer.
It makes so much sense. So the event loop is this bouncer, and its sole job is to stand at the door of the club, which represents the call stack, and just check things out. As long as there are people inside the club, meaning synchronous code is actively executing, the bouncer just waits.
He's just crossing his arms, standing at the door.
Right. But once the call stack is empty, once the CLUD is cleared out, the bouncer steps outside to check the lines to see who gets to enter next.
And this is the crux of the whole issue. There isn't just one line outside this club.
No.
There are two separate lines, and they have completely different security clearances.
Okay, so let's talk about line 1. This is general admission.
Right, the Microtask queue.
The Microtask queue. This line holds things like set timeout, set interval. So if you tell the browser, hey, wait 100 milliseconds and then run this function.
That function goes to wait in general admission?
Exactly. But crucially, this is also the line where the browser's UI rendering events wait their turn.
Yeah, that's the big one.
Yeah. When the browser needs to calculate layout changes or paint the next frame of a CSS animation like Timothy's spinning loading wheel, it has to get in the Microtask line. It's in general admission with everyone else.
But then you have line 2.
The VIP line.
The VIP line, the microtask queue. This line is the exclusive domain of promises.
High rollers only.
Seriously. When a promise resolves its den, or .catch callbacks, don't go to general admission. They are handed a VIP pass and placed directly into this microtask line.
It also holds mutation observer events, right?
Yes. If you have a script watching the DOM for changes, the callback for that observer goes right into the microtask queue. You can even manually put things in there now.
Oh, with the QMicrotask API.
Exactly. You used to see developers write really hacky code like promise.resolve, .then, just to force a function into the VIP line.
I've definitely done that.
We all have. So the browsers finally gave us a dedicated command for it, QMicrotask. But you have to use it sparingly because of the bouncer's strict policy.
Right, the infinite VIP party. This is where things go wrong for Timothy. The bouncer has a very strict rule. VIPs always go first. Always.
Always.
The bouncer will not pull a single person from the macrotask queue.
Yeah.
He will not let anyone in from general admission until the VIP line is entirely, completely empty.
And that makes sense from an architectural standpoint.
Wait, really? Why?
Well, the browser engine wants to ensure that all your internal state changes and data calculations are totally resolved before it repaints the screen.
Oh, I see. So if it didn't prioritize VIPs, it might pause mid-calculation, paint the screen, and accidentally show the user-corrupted data.
Exactly. Imagine a banking app painting the UI when the math for your account balance is only halfway done.
Oh, that would be a disaster.
Right. So the VIP line ensures the underlying data is mathematically stable before the human user ever actually sees it. It's great for state consistency.
But terrible for performance if you misuse it.
Terribly, because if we look at Timothy's code, he didn't just have one single promise resolving. He was processing this massive data set by chaining promises together.
It was recursive.
Yes. The first promise resolves, processes a chunk of data, and then immediately queues up another microtask to handle the next chunk.
So going back to Margaret's analogy, it's as if a VIP gets into the club, and the very first thing they do is text their friends to come join them in the VIP line.
That is exactly what's happening. The bouncer lets the first VIP in, waits for them to finish, checks outside, sees the new VIP friend, and lets them in. Then that friend texts another friend.
It's an infinite VIP party. And the bouncer just keeps letting them in, one by one, because the VIP line never actually hit 0.
And what does that mean for general admission?
They are starving. Timothy's set time out, and the browser's attempt to paint the next frame of that CSS animation, they're just left shivering out in the cold.
They never get in the door.
The rendering engine is effectively starved. The event loop is successfully processing asynchronous code, sure.
It's doing the math.
Yeah, but it never once looks at the macrotask queue. So the screen freezes. Not because the main thread is blocked by one giant synchronous function, but because it's caught in this endless cycle of microtasks.
Starvation is such a frustrating rite of passage for developers. But once you realize what's happening, the fix is actually pretty straightforward.
Timothy has his aha moment. He realizes he didn't just need asynchronous code. He needed to give the event loop room to breathe.
Right, you have to break the recursive promise chain.
So what does he do?
He deletes the massive promise chain, and instead he rewrites the logic to process the data in manageable chunks, say 100 items at a time.
Okay, so he processes a chunk, but how does he trigger the next chunk without starving the queue again?
He uses a set timeout to schedule the next batch.
Yeah. He uses a macrotask strategic.
Exactly. By wrapping the next chunk of work in a set timeout, he is intentionally yielding control back to the browser. He's taking the next batch of work and putting it in general admission instead of the VIP line.
That is so clever. So now, picture the club.
Okay.
The event loop processes the first 100 items via a microtask. When that chunk is done, the microtask queue is finally empty. There are no more VIPs.
Right. The bouncer looks at the VIP line, sees it's empty, and finally looks over at general admission.
And who is standing at the front of general admission? The browser's pending render event. The bouncer lets it in. The browser updates the UI. The spinner rotates a few degrees.
The gray circle springs to life.
Yes. And then the bouncer looks back at the line, sees the set timeout for the next 100 items, pulls that in, and the cycle continues.
It's a cooperative multitasking environment now. The heavy processing still gets done, but the UI actually gets a scheduled chance to update in between the chunks.
Now, I know some people listening might be shouting at their speakers right now.
Saying, just use a web worker.
Exactly. Why not just use a web worker for heavy data processing?
It's a fair point. Web workers are fantastic because they spin up an entirely separate background thread. The heavy math doesn't touch the main thread at all.
Right. You send the data to the worker, it does the math, and it posts a message back when it's done. The UI literally cannot be blocked.
But they aren't a universal fix.
Well,
While sometimes your data processing relies on heavy DOM manipulation, which web workers cannot access directly. They have no concept of the window or the document.
oh, true.
Or you might be in a legacy code base, refactoring an entire architecture to support asynchronous messaging between the main thread and a worker just to fix a frozen spinner bug.
Yeah, your product manager is not going to approve that ticket.
Not a chance. So in those cases, understanding how to manually yield the thread using Macrotasks is an absolute essential skill.
That makes total sense. And before we wrap up Timothy's story, Margaret drops one final technical nugget about making this look completely seamless.
Right, because Timothy used set timeout to yield the thread.
Yeah, set timeout with a 0-millisecond delay.
Which works for yielding, but it's not actually the best tool if you want perfectly smooth animation.
Because set timeout doesn't know anything about the screen's refresh rate.
Exactly. If you use set timeout, that callback might execute at a highly inefficient time in the browser's render cycle.
So what's the alternative?
Request animation frame. It's a special macro task designed specifically for visual updates.
Okay, how does that change things for the bouncer?
Request animation frame basically tells the browser, hey, run this code right before you're about to paint the next frame. It syncs your execution perfectly with the display's native refresh cycle.
So if Timothy switches from set timeout to request animation frame,
Right.
he's not just yielding the thread, he's aligning his data chunks with the browser's natural heartbeat.
Exactly. His loading spinner won't just appear, it will animate as smoothly as mathematically possible.
It's all about using the right tool for the job. You use promises and the microtask queue when you need immediate state consistency.
Right.
You use set timeout when you need to defer non-critical background work. And you use request animation frame when you need perfectly smooth visual feedback.
The core takeaway for you as a developer is that asynchronous is not a magic wand.
It really isn't.
JavaScript's single-threaded nature requires you to actively manage how your code interacts with the event loop. Just wrapping everything in asynchronous syntax doesn't magically make your app performant.
If you don't respect that invisible priority difference, the VIP microtasks versus the general admission macrotasks, you end up weaponizing the browser's own system against your users.
So true. So the next time you're staring at a frozen web page or a button that won't click or a loading spinner that just locks up entirely,
You'll know exactly what's happening behind the screen.
it's not a crashed server. It's an out-of-control VIP party of microtasks that is refusing to let the rendering engine in the door.
Which, honestly, looking at this entire system, leaves us with a really interesting, slightly provocative architectural question to think about.
Yeah, I love this point. Think about what we've just discussed. Our web browsers inherently prioritize raw data processing and mathematical completion, the microtasks, so aggressively over visual user-facing updates, the macrotasks, that they will actually freeze the screen.
They will lock the human out just to finish the math.
Exactly. It forces developers to manually intervene, to build in these strategic pauses and chunking algorithms just to keep the human in the loop.
It really makes you wonder, what does that invisible hierarchy tell us about how software architecture fundamentally values machine efficiency versus the human user experience?
The system cares more about the data being perfect than it does about communicating with the user.
It's written right into the foundation of the web.
But understanding it is the first step to building applications that actually respect the user's time and experience.
Couldn't agree more. Thank you for joining us on this deep dive into the event loop and the hidden mechanics of JavaScript. Keep exploring the architecture beneath your code, and we'll catch you next time.